So we're about to discuss the empirical gas laws. Those are the gas laws that people got by observing the behavior of gases. Empirical means observed or from experimental data. So, but before we do that, I always found it was useful to review some math topics. So the topics in particular are directly and inversely proportional. And this actually helps you realize too that you do have some insight into what gases will do, to example for pressure or for volume. So to give you an example, right? Let's say you have a volume, right? And let's say that volume is inside a balloon. So I have my little balloon like this, right? And then I add moles to it. So what happens to it, right? Well, most of us recognize, that's like blowing into the balloon. Most people recognize that the volume will increase as I add moles to the inside of the balloon. In other words, volume is directly proportional to moles. Now, if I do, for example, temperature, right? And you think about a volume of a gas, again, same balloon, and I have volume, how is it proportional to temperature? Well, most people, again, realize if you increase the temperature, the volume of the balloon will increase, and if you decrease the temperature, the volume of the balloon decreases as well. And you can make the same kind of discussions for pressures and moles and temperatures, temperature and pressure. So there's a bunch of different relationships that are directly proportional. Now comes to the one that people often have difficulty with, and it's called inverse proportionality. And unlike direct proportionality, right, it means that when one goes up, then the other one goes down. So for example, again, I'm going to do just balloons here, right? Here's my balloon. And it has a gas that has a pressure and a volume on the inside. That's the size of the balloon. And then I increase the pressure to the outside. Now, if you think about what happens is the balloon will shrink as I increase the pressure. It shrinks until the inside pressure and the outside pressure are the same, and then it's balanced and it stops moving. So if I add pressure to the outside, right, then you're squeezing that gas down. Then what happens is it goes down in volume, like this. But what happens to the pressure? Well, the pressure on the inside goes up. So this is what we mean by inverse proportionality. Now, like in an equation, the way that looks like is pressure times volume equals something. So if pressure goes up, and this something is a constant, right? If pressure goes up, then volume has to go down. So that's what we mean by inverse proportionality. Another place you can sort of imagine this is in a bicycle pump. In the side of a bicycle pump, you have a piston. It's got a long handle on it, right? And then if you take that piston and you push it down, then the volume goes down, but you know that the gas inside the piston goes up in pressure. So again, inversely proportional to each other. So now what we're going to do is we're going to talk about the empirical gas laws. And before we sort of get into that again, we did the mathematical aside, let me define what the variables are that we use to describe a gas. P is the pressure. Now, you could talk about any units of pressure. Typically, though, it's atmospheres. V is equal to the volume of the gas. N is moles. And T, in the gas laws, this is the first time we have to use the Kelvin scale, but T is the temperature in Kelvin. And I'll talk about a little bit as we go down this list of empirical gas laws, talk a little bit about how that came to be, that it has to be in Kelvin, okay? So here's an example of an empirical gas law. Okay, I'm not going to give it a name yet, but it says if the temperature of a gas increases from 25 to 125 degrees Celsius and initially had a volume of 25 milliliter, what's its final volume? In other words, I'm going to heat this gas, right? I'm looking for V, right? And I know that if I increase the temperature and everything else stays the same, the volume should increase because those would be directly proportional to each other. So what I could write is this. It's a proportionality of temperature. So it's going to be temperature 2 over temperature 1, right? And that's going to be times the volume 1. So volume 2 is equal to temperature 2 over temperature 1 times the volume 1. This is going to be such that when I insert the temperatures, okay, it's going to be the larger temperature over the smaller temperature, and that'll cause the volume in this equation, volume 2, to increase. Again, this is not necessarily how the book does it or how you read about it on the internet or whatever. This is just talking about behavior of gases and using proportionality to help us understand like whether or not volume change will be bigger, and then will also allow us to calculate those values. Now I'll also show you the equation book ways because some people find that a little unsettling to not be able to just have an equation to work. But conceptually, if the temperature goes up, you know the volume's going to go up, and it's always in proportion to the temperature. So that's what I've done here. Okay. So to solve this problem, really, what you can do is you can say, well, V2, and then I have to figure out which one of these is T2, right? It says 125 degrees Celsius. Now we have to convert it to Kelvin. It's okay to use 273. And then divided by 25 plus 273 times my initial volume, which is 25 degrees, or 25 milliliters, like that. So this is going to be equal to 398 Kelvin divided by 298 Kelvin times 25 milliliters. And so I can calculate that as 398 divided by 298, that's my proportionality of temperatures, times 25. And my volume will be 33.8389 milliliters. Now in this question I have two significant figures with my 25, so I'll round it to there, so that's going to be equal to 33 milliliters, like that. So I'll show you the other way to do this, and this is using something known as Charles' law. Charles was a scientist who studied the relationship between volume and temperature. And what Charles said was T1 divided by T2 is equal to V1 divided by V2, like that. So that's, in essence, Charles' law. I'll show you another way to get this equation later as we go through these. But then in this problem, all you have to do then is identify the different variables. So I often tell students, make a little table, right? For example, V and T and 1 and 2. This is just to help keep things organized, right? And then you read the problem, and it says, and I always put temperature at the end because I'm going to have to convert it to Kelvin, and so that leaves me space to convert it. But the volume will be, let's see, 25 milliliters. That's my initial volume, and I'm just going to write milliliters down here so I don't have to put it in the table. And then it's 25 degrees Celsius. So this is 25 degrees Celsius, but I'll add 273 to it. And then it says the temperature goes from 25 to 125, so I'm going to say 125. And this can, again, add 273 to it. And then you notice that when you fill Charles' law's table out, what you find is there's a missing value. This is actually V2. So this is V, right, and this is the subscript 2 here. So now what I do is I take this equation, and now I have to solve it for V2. And so to solve it for V2, I generally just tell people cross multiplies V1 and then T2 is equal to T2 times V1. like that. So I just multiplied the denominators, and then I divide through and I isolate the variable that I'm looking for. In this case, I'm looking for V2, so what I'll end up doing is dividing by T1. The T1s will cancel, and then I'll be left with T2 over T1 times V1, like that. And then go back up to here, you'll notice what happened. It's the same equation that we came up with, but we didn't actually use Charles' law. I don't really care if you know that pressure or volume and temperature is Charles' law. Some people might. It's not really that important. There is one that you need to know, and it's called Boyle's law, and we'll do that one next. So in this problem, we have a volume of a gas, right? And we're being asked to calculate what its volume would be after a pressure change. Now, if you remember, we said pressure and volume are inversely proportional to each other. That is, if I increase the pressure of the gas, its volume will get smaller, right? So I'm looking for V2. And what I'm going to do is I'm going to set it up like this. I know that V2 has to be smaller than V1 because the pressure is going up, right? So in other words, I'm going to write it so this fraction is going to get smaller. So pressure and volume inversely related. So when there's a pressure change, let's say the pressure goes up, then I expect that this number that I'm going to multiply times V1 will be such that the volume V2 will be larger. So I just set up the proportionality in the way that I know the gas will behave. So this will be, right, doing this, 725. The millimeters of mercury will cancel out, divided by 760 times V1, and that's 255 centimeters cubed. So then I just do 725 divided by 760 times 255. And that gives me 243.3. centimeters cubed, and there's three significant figures, so I'll round it to here. So it'll be 243 centimeters cubed. Now, this is known as Boyle's law. This is the one I would like you to remember. I don't care if you remember all the other ones. And it's the relationship between pressure and volume. And when Boyle wrote this law, he wrote it like this. He said P1 V1 is equal to P2 V2. So again, you'll have I give these equations on the exam, or with the exam. What you'll have to do then is organize the data and then solve for the missing variable. Now, I'm not going to tell you it's Boyle's law. You have to read the problem and see what the variables are. So in other words, I'll read a problem like this. I'll say, okay, I'm going to organize my data. I'll have P and V. So that's what I see in here, right? And I see a 1 and a 2. I see two different states. So what's going to happen is I'll say, oh, I have P and V. That's the only thing I've written down up here, so it's a Boyle's law problem. And so what I can do is then solve for the missing variable. So I have a gas volume of 255 that goes here. And that's in centimeters cubed. So I'll write it like that. And then it's at a pressure of 725 millimeters of mercury. And then what's the volume when it goes to 760? So I'm going to put 760 here. I should probably put a line there. And then what I'm looking for, you notice this missing value is a volume, right? Just by the way the grid is laid out. If a gas has a volume of 255, right, what is the volume at 760? So that's really what I'm looking for. So I'm looking for V2 in the equation. Again, this is the volume. This is the second state of the gas, is what we would say. So what we can write is take this equation and solve it for V2. So I'm going to go V2 is equal to P1 V1 over P2. And I just divided by the P2 to get it out of the way. Remember, you have to isolate the variable you're looking for. And so now you can plug in P1 is this value, 725. V1 is 255. And then the bottom number, P2, that's down here, is 760, like this. Now, I forgot to put units in here, but I just want to show you this. This is millimeters of mercury. And this is millimeters of mercury. And then with the 255, I have centimeters cubed, like this. So you notice what happens, because the top number is in millimeters of mercury and the bottom number is in millimeters of mercury. Those actually just cancel out. And as long as the pressure units are the same, you can cancel them out, and that's not a problem. The only time that doesn't work is with Celsius and Kelvin. It has to be in Kelvin. So you always have to convert that one to Kelvin if it's not already in Kelvin. But the other ones, all the other variables, the P, V, and the N, those can be in any unit because they will cancel out as long as you keep them the same. Moles could also be grams as long as you keep the grams the same, because grams is proportional to moles. So now again, I'll plug this into my calculator, but I'll get exactly the same answer, because you notice what happened. The way I wrote this, right, this is P, the 725, P1, times V1, the 255, right, divided by 760. So you can either set up the equation, or you can sort of intuitively come up with the relationship knowing the way gases behave, and then solve the problem that way. So this next one is one that we call the combined gas law, where it basically just means we changed a whole bunch of stuff. But we'll read the question. It says you have 1.5 moles of gas, right, and it has a pressure of 35 psi and 26.5 degrees Celsius. If 2 moles of gas are added and the temperature is decreased, what is the final pressure in the container? So again, this is going to be a series of proportionalities. I'll always start with my P1, right? That's going to be my 35 psi. And then what will happen is I'll have to multiply that by proportionalities. For example, it goes from 1.5 moles to 3.5 because I added 2 moles, right? So adding moles should make the pressure go up. And so you would say 3.5 divided by 2, or 1.5, sorry. So this is going to be moles final over moles initial. Now what does temperature do, right? If the temperature goes down, right, you expect the pressure to go down. So the way I'll do my proportionalities for my pressure is or for my temperatures is I'll say, well, I want it to be a smaller number at the end. So this will be 10 degrees at top and then 26.5 degrees Celsius at the bottom. Now, and I'll have to convert those to Kelvin, right? But think about how we've just done this. We've just said, well, I have this pressure, and I made this change in pressure that's going to make the pressure go up. So I set the proportionality so that it'll go up. And then I decrease the temperature, which should make the pressure go down. So I set my proportionality so the temperature would cause a decrease in the final pressure. Now I have to add 273 to both of these. And now that's in Kelvin, and then I can solve this problem. So this will be 35 for P1, right, times 3.5 divided by 1.5. Now I'm going to simplify this because I'm going to cancel those out. Times, and then that's going to be 283 Kelvin, and then divided by, and then 26.5 plus that. That'll be 299.5, and this is Kelvin, so the Kelvin will cancel out. So now what's left is to plug it into my calculator. This will be P2, and then I'll just run this calculation. This is what's equal to P2 up here. And this comes out to be, I just did the calculation, I think didn't think you need to see me type it in, right? But 35 times 3.5 divided by 1.5 times 283 divided by 299.5 comes out to be 77.2 psi. And I only have, well, I really only have one significant figure, so I should really round this to 80 psi like this. Okay, so let me show you the form of the combined gas law. The combined gas law basically says this: P1V1 divided by P2V2 is equal to T1 over T2. Now, when you see this, like if you look up the combined gas law, it's not usually laid out like this. Oh, sorry, I left my N out. There's an N here and an N here. It's not usually laid out like this, but I like it this way because it's sort of it's more organized than what you normally see. So then what I have to do is I have to make a table, and I'm going to go like this. So I'm going to have P, right, V, N, and T. And then I'm going to go ahead and plug in 1 and 2 here. Those are my states, right? So again, I'll go into the problem and I'll say, well, I have 1.5 moles of gas here, so I'll have to do 1.5 here. And it has a pressure of 35, right? And then it's at 26.5 degrees Celsius. Oh, I didn't mean to put that line there. 26.5 degrees Celsius. I automatically add 273 to that. And then I'll say for, let's see, state number 2, it says 2 moles of gas are added. So this gives me 3.5, right? And then T2 will be, but the temperature is 10 degrees. So I go 10 degrees Celsius plus 273, like that. And then what am I asked for? What's the final pressure? Now you notice there's a volume here too, so you could actually do volume changes, but since it's not mentioned, then we just cancel it out. We assume the volume is constant, and so we'll cancel it out. So now what we can do is we can write our equation like this. This is telling us our equation is P1V1, P1, because my volume's canceled out, P1 over P2 is equal to N1 T1 over N2 and T2. That's this equation without writing the volume in because nothing was given about the volume. Now what you have to do is you have to solve it for P2. So to solve it for P2, again, the simplest thing for most people is just to cross multiply to get the numbers out of the denominator. Get the numbers out of the denominator, and so I'll say P1 times N2 T2 is equal to P2 times N1 T1, and I'm solving for P2, so I'll divide 1 by N1 T1, like that, and then I can go start looking for my values. Now I just want to show you this though, right? N2 is 35, right? And N1 is 1.5. Or sorry, 3.5 and 1.5. You notice that's what this is in the equation. It's the ratio of moles that we used when we did our calculation. And this is actually the same ratio of temperatures that you find here. It's T2 over T1. So again, you could really choose to do it either way. A lot of people are just more comfortable with just putting it in the equation, but you do have to be good at equations. And the other way is use what you know about the behavior of gases to predict what the behavior will be, like know what the pressure will change like, or know what the volume will change like. Now, there's lots of these laws. The only one I really care that you know is called Boyle's law. Maybe you should know Avogadro's law too, but Boyle's law is the only one that you need to know. It's the pressure-volume relationship. We did a Charles law, and this is kind of a combination of an Avogadro's combined gas law as well. All right.